This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hello everybody, good afternoon, and welcome to our final lecture on algorithms for functional genomics. And this week we've been talking about supervised learning, and today we'll talk about model selection and validation, basically how we best validate models and select between them. And so on Wednesday we discussed supervised learning, and the main goal of supervised learning is something called generalization, which is different from memorization. So generalization is the ability to predict on unseen data, and this is the main goal of supervised learning. And we also discussed about two specific phenomena, underfitting and overfitting, and we want to avoid them. And today we'll discuss how. And we also discussed on Wednesday a few learning algorithms, which are definitely not an exhaustive list, but they are interesting algorithms that have been out there for a while. So we discussed about KNN, which is a distance-based one, a probabilistic one, which is naive-based, decision trees, support vector machines, and we also talked a little bit about ensemble methods. There are other methods that we haven't discussed, for instance, neural networks, and they are very relevant, for instance, if you're interested in deep learning. And also we only covered in this subject supervised and unsupervised learning. However, the area has grown to other things like reinforcement learning, transfer learning, and so on and so forth. If you're interested in it, you can either chat with me afterwards, or there are also different machine learning subjects offered within the university as well. So today we're going to talk about model validation. And specifically, we're going to talk about two different strategies. One is called holdout validation, and the other one is cross-validation. And we're also going to talk about evaluation metrics, how to choose the best performing model. For classification, we're going to mention confusion matrix and discuss about type 1 and type 2 errors. We're going to talk about ROC, ROC curves, and how to deal with unbalanced and balanced data. And for regression, we're going to mention a couple metrics that are widely used as well. And I'm just going to touch on a few tools and packages that you could use if you're interested in supervised learning. So we want to do performance estimation. If you remember, there are three main components for supervised learning: the data, the features we calculate from the data, and the actual learning algorithms that will try to identify combinations and links between the features and the data we have. So the question is, how do we know that our model is generalizing? So it's predicting well on unseen data rather than just simply memorizing the training data we have. And what we want to answer is actually, how do we select a good predictive model? How we choose from different models? Perhaps we need to try a different algorithm. If you think about these three components, one thing could be you're not choosing the adequate algorithm for your data. Perhaps you're not using enough data, or your data doesn't have high quality enough. So if you remember something I mentioned, your predictive model will only be as good as the quality of your input data. So perhaps you need to revise that, or perhaps you need to investigate different features. For instance, if your model is underfitted, perhaps it's just using a feature set combination that is not powerful enough. It doesn't explain the overlaying principles and phenomena. So in performance estimation, what we want to do is avoid overfitting and underfitting. Okay? Underfitting is when your model is not flexible enough to account for the whole variability of the data. Overfitting is too strict to the data you have, so it's just memorizing it. And for that, we need a very robust validation strategy. And this has to do with choosing the right performance metrics as well. So if we want to estimate generalization performance, we need to predict performance on unseen data. That's one thing, since that's the main purpose of supervised learning. And we need to be able to choose the best performing model, which is comparing them and choosing the most appropriate one. And for that, we'll have different evaluation metrics. So choosing the best model is a combination of validation, so predicting it on unseen data, and also being capable of assessing a predictive model's performance. And that will require us to assess different algorithms, different parameters for these algorithms. For instance, if you're using K and N, what's the best value for K for you? If you're using SVM, what is the most appropriate kernel function for you? And feature combinations as well. Okay? So that's what we are going to discuss today. And we need to do that in a rational way. It's not just about, oh, you input some data, there's some math magic going on, you get a response. What if it's wrong? Well, just stir up the pile, try something different until it looks right. We're going to do something more rational. Okay? So model selection and validation. And if you recall the pipeline, the general pipeline for supervised learning, we have here the three main components. So we have our data, we are going to do feature engineering, and we're going to train on our data. And we usually divide our data set into three. Training, that we use to actually fit our model to our data, a validation set that we use to assess performance during training, and a completely independent test set, which is usually called blind tests. When we divide our data set into three groups like this is actually called holdout. Okay? So it's one type of validation. So holdout validation, basically, it's important because we can't use the same data we train on the test model. Okay? So if you use the same data points to train and to test the model, that's called cheating, right? So if the purpose is to predict unseen data, we need to hold out some data. And then we need to have a test model to test the model in a different data that it was trained on, and this will give us an unbiased estimate of the learning performance or the generalization performance. Okay? So a holdout validation is basically when we divide our data set randomly into three different subsets, which are highlighted here. So the first one is the training one, which we use to build the predictive model. The other one is the validation set, on which we assess performance during training, and we can use that validation set to either select the best algorithm or select the best parameter for the algorithm. So imagine if we're doing a classifier for a given problem, and we decided to use naive Bayes, right? So the first thing we need to do is to train a model based on a training set for a naive Bayes. Do you recall what naive Bayes would do? So naive Bayes is basically going to try to calculate the conditional probability of a given subset belonging to a class. Is going to try to find the most likely class. So for the training data set points, it's going to calculate all those probabilities, and that's our trained model. So the validation set will come then on a prediction. So for a given set of features, what's most likely data. And since we have the actual answer, so since it's this supervised, we have labeled data, we can calculate a performance metric on the validation set. And this could guide us on selecting different algorithms, different parameters. And we always have an independent test set, which will train our data on the whole set and then assess the performance on an unseen, completely unseen data. And so what if the performance on training here is much better than performance on test? What is this called? Overfitting, right? And that's what we need to avoid. And so the holdout global strategy looks like this. So you have your complete data set, right, of labeled data, together with the features you calculated, and you want to provide this to a learning algorithm. So the first thing you do on the holdout strategy, you split your data into three. So train, validation, and test. Train in blue, validation in yellow, test in green. What's the percentage of data points per test set? That varies depending on your problem. Basically, this is highly dependent on the amount of data you have, the problem you have. Let's say we're considering 70% for training, 15% for validation, and we have an independent blind test of 15%. Okay? Second step will be then train a model on our training data. And we can train our model varying parameters for different algorithms, and we'll then assess the performance of that model on our validation sets, and we'll compute a validation metric that we're going to discuss. There's several options for validation metrics. And basically, we're going to do this for different parameters and for different algorithms. And this will guide us to choose what's the best combination. And then what we're going to do is we're going to combine the train and the validation, retrain the model and the whole data and evaluate it on the blind test. Okay? And this will give us a test-independent metric. And then we're going to compare this metric with this metric. Hopefully, they will be comparable. And then we will avoid overfitting. And this will give us an unbiased estimate of the generalization of the model. And this is basically the overview of a holdout strategy for validation. Okay? Any questions so far? What's the problem with this? What's the main limitation when you just split randomly your tests and your data sets and just say this is training, this is validation, and this is test? Can you think about one possible scenario that this is probably not a good idea or might not be? If you have the number of data is relatively limited and you make a selection, maybe out of luck, you select for your validation set data points that you can easily classify that will then make the performance on validation overestimated, right? So this is called selection bias. You can just get lucky on the way you select your data. And what you do for that, you repeat the process multiple times. So one thing you can do is a repeated holdout validation process. So you divide train and validation multiple times, let's say 100 times, 1,000 times, and you calculate the metrics per run, okay? And hopefully this will dilute any selection bias you have, okay? Because the problem is when you have one distribution of the data, and because either you're very unlucky or you have not that much data, you might end up with a different distribution. So if you train on one distribution, you test on the other, that's very unfair, okay? And you can do either a repeat holdout validation, or you can do something called bootstrapping. Bootstrapping in this particular scenario means you're doing your resampling with replacement. So you put the data sets back. So let's say you have your original data set, and you're selecting on your first bootstrap iteration, you put 3 out as your test set, and out of the 7, you select 10 again. So you can have repetition here. This is to make sure the probability doesn't change. So if you keep selecting randomly items from here, so the probability will change. So you have a higher probability of having or drawing the following one. So that's the idea of bootstrap. You're keeping the probability of picking one the same. Okay? So you can do holdout validation, but it's probably a good idea to repeat it several times. Alternatively, what you can do instead is something called k-fold cross-validation. And the idea behind k-fold cross-validation is to partition our data set into k equal size subsamples, which are called folds. So instead of dividing, this is my training, this is my validation, I merge these two together and divide them into k folds. And what we're going to do is, iteratively, we're going to use one of the subsets as a validation, and all the remaining k minus 1 put together as a training set. And will vary in each round which one is the validation set. Okay? That has a very interesting property that every data point will eventually get on the validation set, and it only gets in the validation set once, and will be on the training set k minus 1 times. And for each round, we can then calculate the performance metric, and overall, we can average the metric per fold. Okay? This will have the effect of reducing bias, so you're using most of the data for the training, but also reduce variance as all the data is eventually used for validation. So if you do one holdout validation, and let's say using 30%, 70% of the data is never used for validation, while on k-fold, you guarantee every single data point is used as a test set. But however, we still need to separate out of this an independent test set. Okay? So the global idea of k-fold cross-validation is the following one. So we're going to set aside, first thing our test set, our independent blind tests, and we're going to split our training. So instead of calling training and validation, we merge everything together, and we split them into k-folds, more or less the same size, ideally at the same size. Okay? And what we're going to do is, the common values for k are either 5, 10, or 20. And what's the effect of k in the size of the training set. If I increase k, I'm training with more or less instances? More. More, right? So if k equals 5 means, let's say this one is our validation set. We are training with 80%, testing with 20%, so validating with 20 in each round. If our k is 10, it's 90%. If k is 20, we're training on 95% and evaluating on 5, but doing this multiple times. So what we do then, after then dividing this into multiple folds, is for each iteration, let's say, we train on the other folds. Let's say k equals 5, so we have 80% of the data here. We're going to train on this, and we're going to evaluate the performance on fold 1. This will generate a given performance metric, or several ones. And then we're going to use fold 2 as evaluation, train on the rest, and so on and so forth, and then we'll end up with k metrics, and we average them out. And we can repeat this whole process per parameter, per algorithm. Okay? And we'll select the best one. And we'll then combine everything together, so the whole data set will refit our model, retrain our model, and then assess the performance on the blind test. And we, again, can compare performance between cross-validation and blind tests. Okay? Is that clear? So then you have two strategies to validate your method, which are very robust. Okay? We are always then evaluating generalization on the blind test. And any specific type of cross-validation, depending on your data set and your problem might be relevant, is leave one out cross-validation, which is quite self-explanatory. So leave one out, you leave one out per round. So if you have 10 instances, 1 is validation, 9 are used in training. You keep varying which one is for validation until every single one has been in validation exactly once. Okay? And basically, what this does is maximizes the amount of information available for training. And this could be quite useful if you don't have that much data. If you're dealing with a few thousand, few hundred data points, this might be interesting for you. So you maximize the amount of information you can train, but still you validate every single data point you have. Okay? However, this can be quite computationally intensive. So for each of these rounds, imagine you can vary the value of k if it's k and n. You can vary different algorithms. So if you have 1,000 points, you're going to do this 1,000 times per parameter per algorithm. Okay? So it's something to bear in mind. But if you have small data sets, it might be interesting. Okay? And then, since we know how to validate a specific predictive model, we need to be able to compare them. So how do we select the best performing model? And for that, we have different predictive performance metrics. And we're going to talk about a few of them here. Again, this is not going to be an exhaustive list of them. Okay? And we want to compare performance on the validation sets. And hopefully, the performance on independent test set will be consistent. That's our goal. Okay? And there are multiple metrics, as I mentioned, for both classification and regression. And we'll start off with classification. And most of them, at least those that we're going to discuss today, are derived from a confusion matrix. What's a confusion matrix? Can anyone tell me what's a confusion matrix? It's a matrix. Very confused, but not really. So it's a very simple thing. So it's a table layout of our predictions. So let's say you have a binary classifier, right? So you have two options, yes or no. What are the possible outcomes? You get the yes right, you get the yes wrong. You get the no right, you get the no wrong. That's basically a confusion matrix. So the rows on the confusion matrix represent the predicted class. And the columns represent the instances that are actual classes, so the real labels that we already have. If you change predictive with actual, that's not a problem, right? But here, let's consider the rows as predicted, the actual columns as actual. And for binary classification, then we'll have two classes. Let's call it positive and negative, and we'll have 4 components. So the first one is true positives. So true positives are then items that have been correctly predicted as being a positive. So a true positive. I predict it as positive, and it really is positive. okay? For instance, if you have a test for cancer, a cancer test correctly identifying a patient who has cancer, that's a true positive, okay? What about a true negative? So correctly classified instances that belong to the negative class, which would be here. So these diagonal are the success cases that we hopefully want to maximize. And we will hopefully avoid the red diagonal, okay? So a true negative in a cancer test is when your cancer test correctly identify the patient who doesn't have cancer. Good. What about the errors now? So we have false positives, which is also called type 1 error, which are incorrect predictions belonging to positive class. So these are false positives here. So in an instant I said it was positive, but it wasn't actually. In the context of a cancer test saying a patient has cancer, however, they don't have. Okay? A false negative, which is also called type 2 error, will be incorrectly predicted instances belonging to the negative. Okay? So I said this was no cancer, however, it is. So basically misdiagnosing a patient and dismissing them, saying, go home, but you have cancer. So that can be quite complicated. So what we want to do is basically minimize the false cases, red diagonal, maximize the true cases, green diagonal. However, which type error is worse? Type 1 or type 2 error? Which one? 2? Maybe on this case, but that depends on the problem, right? Depends on what you want to maximize. Certainly on a cancer test, saying someone has cancer and they end up not having cancer, that's not as bad as missing it, right? But it varies, and we're going to discuss one example that actually type 1 error is worse. So type 1 error and type 2. Let's give it another example. Let's say you have a fire alarm, right? So fire alarm is supposed to ring when there is a fire. So the 4 possibilities we have is fire alarm rang, there's a fire, good. That's a true positive, it's working properly. Other possibility is it rang, but you just burned toast. So there isn't fire, so that's a false positive, considering then fire as our positive class. The other possibility is it doesn't ring, well, there is no fire. So this is our true negative. And then our false negative, it didn't ring, however, there was a fire, and you need to be more careful in the kitchen. In this case, it's clearly to see that the worst case scenario here are false negatives. So if you're building a predictor, you might be interested in minimizing false negatives. There's always a compromise between the two. So type 1 error will be fire alarm rings when there is no fire. Type 2 error will be fire alarms fails to ring when there is one, okay? Which in this case is more serious, and we'll try to avoid. And if you recall, a few weeks back when I was talking about mutation analysis, I mentioned that most pathogenicity predictions have a tendency to have a lot of false positives, and just basically overestimating the number of pathogenic mutations, because it's better to say this is pathogenic, and in fact it isn't, rather than missing one and misdiagnosing a patient, for instance. So we're going to discuss a couple performance metrics now. And the first one, and probably the most common one, and the most misleading one, is accuracy. Okay? So this is the one people use in the wrong way more often. So accuracy is a very simple concept. It's basically the number of correct predictions I have overall, which is basically our true diagonal. So true positives plus true negatives divided by the total number of instances I have, right? When can I use accuracy? Usually it's an okay metric when the 2 classes have nearly the same number of items, okay? And when not to use, well, unbalanced data sets. Why? Imagine you have the following. So 95% of the data is cancer cases for your cancer tests, and 5% are not cancer cases. What could happen here? Can you imagine a very simple classifier that gets a very, very high accuracy? How would you do it? You just say everything is A, everything is cancer. That will render a predictor guessing everything as class A with 95% accuracy. Say, wow, that's amazing. That's not predictive. That's not generalization. That's just a reflection of the natural distribution of classes. Okay, so accuracy in that case wouldn't be interesting. And a take-home message would be then there is no silver bullet in terms of metrics. You always need to use a combination of them and never accuracy alone. The second one is precision. And precision is basically the proportion of predicted positives that are actually positives. So true positives divided by positives, which are RO. Everything your classifier says is true, is positive. The truths and the false ones, okay? And what instantly you can see is that precision will take into account type 1 error. So perhaps if you want to minimize type 1 error, you might want to maximize precision. It's a valid evaluation metric when you want to be very sure about the positive class prediction, okay? Example when this could be applicable. So let's say you're building a system for a bank that wants to predict whether a client needs to have their credit limit decreased. So in this case, we want to minimize false positives, which is the case you have decreased the limit unnecessarily, because that would generate a lot of customer dissatisfaction. So in this case, you want to minimize type 1 error and perhaps maximize precision. Okay? Another metric is recall, also called sensitivity. And recall is the proportion of actual positives that we correctly classify, which you can think of as a recovery rate. So recall is basically true positives out of everything that is actual positive. So a true positive is a positive that I say, yeah, it's positive. But a false negative is in fact a positive, isn't it? So the actual column, which is this, so we basically get the proportion of true positives out of the actual column, okay? So in this case, recall is taken into account type 2 error and is used when you want to recover as many positives as you can. So if you want to predict if a patient has a disease or not, you want to maximize recall, minimize type 2 error, and in order to avoid discharging a patient that actually needs treatment, for instance. So what you want is minimum false negative, maximizing recall. But usually these two will go together. And there is one problem, inherent problem with recall, which is, what's the problem with just maximizing recall? If you think about it as a recovery, so everything, I want to recover the positives. What's a way to create a classifier that has really, really good recall? Predict again everything. So if you predict everything as being positive, you have a recall of 100%. It will be a terrible classifier, but it will have a really good recall. Useless one, but it will have a really good recall. So you need to be careful. And usually what we do is we balance out precision and recall. They usually go together. And for that, we will have something called F1 score. How do we balance them? How do we guarantee that they are compatible? So one way to find a compromise between precision and recall would be simply averaging them, arithmetic mean. So precision plus recall divided by 2, right? Let's say we have a predictive model with 20% recall and 100% precision. This is very, very different, right? However, if we just do the mean, we'll have a 60% average, which doesn't quite show the difference between them. And an alternative for this is using, instead of the mean, using the harmonic mean between precision and recall, which is called F1 score or F1 measure. So F1 measure is 2 times precision times recall divided by the sum. And in this case, instead of 60, you would get 33%. So what F1 score does is penalize large discrepancies between these two metrics. Okay, so you want a balance between precision and recall, we usually assess F1 score. Okay? And the second to last classification performance metric has to do with something most of you have encountered before, which is called receiver operating characteristic curves, or ROC curves. Has anyone never seen a ROC curve before? So everybody has seen a curve before. So what's a ROC curve? It's basically a graph showing the performance of a classification model considering different thresholds. And you can understand these thresholds, for instance, as class probabilities on your naive Bayes classifier, and you vary that cutoff you need to classify specific data points. And basically what you're going to have on your y-axis is recall, also called sensitivity, or true positive rate. So yeah, there's a lot of synonyms for the same metric. And on the x-axis, false positive rate, or 1 minus the specificity. In a ROC curve, an interesting metric for a classifier would be the area under the ROC curve. So a perfect classifier will have an area of 1, while a random classifier will have an area around 0.5. So you're basically guessing one class and the other, considering the number of instances per class is more or less balanced. It's basically flipping a coin. It's the probability of getting it right. If you have more or less the same one, it will be 50%. So you have a random classifier here. And you want it as close to 1 as possible. Can you have a classifier with a AUC of 0.1? So below random? Is that possible? Or let's say 0? Yes, you can, but you can convert it to something over 0.5. Yeah, so let's say you have the worst ever classifier. It miscalculates everything. What you do, you just invert the prediction. If you invert the prediction, you go from 0 to 1. Okay? And that's why even if your classifier, you train it, is 0, 2. If you invert the labels, you're probably going to get something close to 0.8. Okay? And the last performance metric for classification is called Matthews correlation coefficient. And is a very interesting metric because it takes into account everything in the confusion matrix. So it's going to take into consideration the truths and false negatives and positives. And it's considered a balanced metric. Therefore, it's a really good metric when you have imbalanced data sets. So the difference in numbers per class is quite different. One of the metrics you can use, of course, you're never going to use just one, but you can use MCC, even when the classes have very different sizes. In contrast with accuracy, you couldn't use accuracy for imbalanced classes. So MCC will range from -1 to 1, with 1 having a perfect prediction, and 0 a random prediction, and -1 indicating complete disagreement. Again, if you have a negative one, if you invert the labels you have, you end up with a positive one. Yeah?
Are all these only good for binary classification?
You can calculate most of them for multi-class classification as well. So what you can do, for instance, with precision and recall, you can calculate the precision per class, the recall per class. If each time, let's say, you have cancer, no cancer, let's say, low, medium, and high risk of cancer. And for each of them, or each time you consider, well, high risk is my positive, you calculate precision. Now, mid risk is my positive, you consider precision, and again with the other. And then you can either take all of them into account, or you can average them out. And there are two ways to do it. For instance, there is called micro, and macro F1, or precision, sorry. And the basic difference between them, you can usually do an average between the number of classes. So you average based on the number of instances you have per class, or you do a simple average between them. Okay? But usually, most of them are available for binary. If I'm not mistaken, MCC is just for binary, but you usually will use a combination of them anyway. Okay? AUC, for instance, you can calculate for multi-class as well. And that's MCC. What if you have, instead of labels, numbers? What if you're doing regression? What can you do? And one of the things you can do is called mean square error, which is basically the average of the squared difference between our predicted value and our actual value. Okay? Alternatively to m squared, you can do m absolute, which is just the difference without the square. Okay? And they're both valid metrics. And in this case, we want to minimize the difference between predicted and actual. And the second one is called Pearson correlation coefficient, which is a measure of linear correlation between two variables, in this case the predicted and the actual. And Pearson correlation also varies from 1 to -1, with 0 presenting no correlation at all, 1 representing a perfect positive correlation, -1 representing perfect negative correlations, and so on and so forth. Okay? So you usually want to maximize your Pearson correlation. And again, if you multiply your prediction to -1, you go from a -1 to a +1. Okay? So you can always convert from negative to positive in the same way you can in classification. So let's think about these two models then. Which of these models is the best one? We're sticking with the case that we're building a classifier to see if a patient has a disease or not. And these are two confusion matrices for model 1 and model 2. In both cases, we had 600 patients that were classified. Consider this as a blind test. So we're just assessing performance on these two confusion matrices. So which one is best? So what's the, let's say, precision of model 1? How do we calculate precision? Let's see how good your short-term memory is. Mine sucks. 200 true positive divided by 250, which is everything I predicted as positive. So true positive plus false positive, which is 200 out of 250, 80% precision. What's the recall of model 1? It's the recovery, isn't it? So it will be 200 out of 300, which is 0.66, 0.667, and so on and so forth. So I'm not going to ask you to do this. I might do in the exam. I don't know. Maybe, maybe not. Let's say we have this range of predictive performances here that we can easily calculate from the confusion matrices. And if you look at this, both methods have the same accuracy. Both methods have the same MCC. One of them has better recall, the other one has better precision. One of them has better specificity, the other one has better F1 measure. So if you look at all of this, they're kind of, there's a compromise between them, right? But which one is the best? So if you consider we have 6 performance metrics for 2 models, model 1 wins on 3, model 2 wins on 3. What now? Which one is the best one? There are multiple interpretations for best one. In this case, which one? Which one? Which model is the best one? If you have to implement this in a clinic for predicting cancer, which one would you use? Second one? Why? High recall. Yeah. In this case, there's a compromise between the two. So model 1 has better precision, so less type 1 error. Model 2 has better recall, type 2 error. So depending on the circumstance, you could choose one or the other. You choose type 2 because you know the context. You know that you don't want to send people home while they have cancer, right? So choosing the best performing metric, choosing the model requires also knowing about your problem, right? It's not just about maximizing a metric, okay? And just to touch on a few things, if you want to pursue supervised learning, there are a few tools of package that I recommend that you start with. The first one, my favorite one, is scikit-learn, which is in Python, and it's built on very robust sets, not only for machine learning, but also for data analysis and visualization. It's open source and has a huge community behind it, so a lot of documentation on scikit-learn. The other one is TensorFlow, especially if you're interested in deep learning. It's developed by Google. And the other one, which I actually started on a long, long time ago, I'm old, is Weka, which has a graphical user interface. So if you just want to play around with your data, that's a good one to start with, and then you move into something like scikit-learn. Okay? Just a few pointers if you're interested in this. Weka is in Java, so Yuk. And just a few final remarks. So we reached the end of this subject, student experience survey. So I've been asked to ask you again, please complete it. Do it now. If you haven't, grab your phone, your laptop, do it quickly. And if you're listening to this via lecture capture, please do it too. Our final exam is approaching. You guys will have 3 hours to do it, plus reading time. We'll have about 20-something questions. There will be multiple choice, short answers, long answers. I think the length is more than adequate. All content covered is examinable, but the focus is demonstrating and that you understand the main concepts we tried to cover. Okay? If you're interested in bioinformatics, computational biology, research in general, just drop me a line. I'm always keen to talk about this stuff, and our group has several positions available for people wanting to pursue PhDs. Yeah?
So how about the case study?
Oh, what?
Case study.
It's part of the content, so yeah. Take a look at that. Yeah, but again, it's about the concepts. And yeah, I think that's all. Thank you very much. It's been a pleasure. I'm gonna miss you all.